Hello dear students of plus 2 medical and non-medical respected teachers. Today I am going to discuss an important topic which is known as magnetic force due to a conductor carrying current placed in an external magnetic field. So suppose we have a conductor of length L placed along x-axis and current I is flowing in this direction, that is along x-axis. That magnetic field is along y-axis and this is z-axis. So that x-axis, y-axis, z-axis are mutually perpendicular to each other and conductor is lying along x-axis. So current is flowing in the x direction. Let A capital A is equal to area of cross section of the conductor, L length of the conductor, capital I is the current flowing through the conductor. Let small n is equal to number of free electrons per unit volume of the conductor. Now consider a small current element of length dl. Direction of current element will be in the direction of current. This is the idl is the current element. Let Vd is equal to drift velocity of free electrons, which is always opposite the flow of electric current. So each free electron will experience magnetic force under the influence of magnetic field. So magnetic force experienced by each free electron is given by minus E into Vd cross B. Where Vd is drift velocity, B capital B is the magnitude of magnetic field. The total number of free electrons within the conductor of element of length dl, that will be n into adl, where adl is equal to volume of the element. So therefore, net force experienced by the current element is equal to df vector is given by minus neadl, that is total number of free electrons into charge upon each electron, into Vd cross B vector. So since I repeat, each free electron of the conductor will experience magnetic force. As a result, the element of length dl will also experience magnetic force, and hence total conductor will also experience magnetic force. So first we calculate magnetic force experienced by each electron, then magnetic force experienced by current element of length dl, which is given by minus neadl into Vd vector cross B vector, or df is equal to minus dq, this is total charge that flows, Vd, the velocity is defined as rate of change of displacement, so minus dl by dt cross V, minus minus cancels, so df is equal to dq by dt, dl cross B. What is dq by dt? Nothing but electric current, so I into dl cross B. So df vector is equal to I into dl vector cross B vector, gives the magnetic force experienced by a small current element placed in the magnetic field B. Now to find total magnetic force experienced in the whole conductor of length L, F is given by F is equal to I integrate dl cross B, or I integral dl will be L because B is uniform. So it will be I into L cross B, or F is equal to BIL sine theta. So which is the required expression for magnetic force experienced by a conductor carrying current placed in a uniform magnetic field B, where theta is the angle between L vector, which is in the direction of current, and B vector, or you can say angle between direction of current and magnetic field vector. Now, direction of magnetic force is given by Fleming's left hand rule or right hand thumb rule, or you can say right handed screw rule. So right hand screw rule because x-axis toward you, like this, current is toward you along x-axis. So it means L vector is along x-axis. So L cross B curl your fingers from L to B, L cross B. This thumb gives direction of magnetic force. That is, magnetic force acts along Z axis. Or you can use Fleming's left hand rule. What is Fleming's left hand rule? Your first finger points in direction of magnetic field, central finger gives the direction of current, thumb gives the direction of magnetic force. And these three fingers should be mutually perpendicular to each other. So, first finger magnetic field, current along x-axis, thumb gives the direction of magnetic force which is acting along z-axis. So, in this way we can find direction of magnetic force. Clear? No. Special cases, when theta is equal to 90 degree, that is the angle between, in this case, current is along x-axis, displacement vector is along x-axis, so angle is 90 degree. So sin 90 will be 1, so F is equal to BIL is equal to maximum. So magnetic force experienced by the conductor is maximum when it is normal to the magnetic field. If theta is equal to 0 degree or sin 0 is equal to 0, F is equal to 0. If conductor is lying parallel to the magnetic field, then there will be no magnetic force. So magnetic force experienced by a conductor carrying current placed parallel to the magnetic field is always 0. But when it is placed perpendicular to the magnetic field, it will experience maximum magnetic force. Clear? Now, we come to force between two parallel. Now, since every wire carrying current placed in a magnetic field will experience magnetic force. Therefore, when we have two parallel straight wires carrying current, then how will they interact each other? So, two parallel wires carrying current in the same direction or opposite direction, they will interact each other. We have to prove when two parallel wires carrying current in the same direction, they will experience force of attraction. Whereas when two parallel wires carry current in the opposite direction, they will experience force of repulsion. In other words, two parallel wires carrying currents in the same direction attract each other, whereas two parallel wires carrying current in the opposite direction repel each other. How? Suppose we have two wires P and Q having currents in the same direction, they say upward. Suppose small r is equal to distance between the parallel wires, perpendicular distance. Let I1 and I2 be the currents through the wires. I1, I2 be the currents through P and Q respectively. Now, find, now each wire will exert magnetic field. Each wire will produce magnetic field around it. Now, suppose P1 is the point lying on wire Q, P2 the point lying on wire P. Then magnetic field due to wire carrying current I1, that is wire P, will be like this. By right hand thumb rule, it will be directed inward. When point P1 lies to the left of wire P, magnetic field will be directed inwards. If magnetic field directed inward, then by using Fleming left hand rule, Fleming left hand rule, first finger magnetic field, central finger direction of current, thumb gives the direction of magnetic force, so magnetic force will be directed towards wire P. Similarly, magnetic field due to wire Q on wire P, that is at P2, will be directed upward. It will be directed upward. So now force will be like this. Magnetic field directed upward, current. So force is again towards wire Q. It means both the forces are mutual and they are acting inwards. So it means two parallel wires PQ carrying currents I1, I2 will attract each other when currents are in the same direction. Now, what happens when two parallel wires P and Q have currents in the opposite direction, I1 upward, I2 downward? Again, suppose P1, magnetic field due to wire P at Q will be directed inward, and magnetic force will again be towards right now. So magnetic field directed inward. Find direction of magnetic field like this. Let us check. Clear? Magnetic field inward, current downward, thumb is the direction of magnetic force. It means magnetic force is outwards. Similarly, magnetic field due to wire Q on P, that is at P2, will be downward again. In this case, by right hand thumb rule, it will be downward. So magnetic field downward, current is upward, thumb is outward. So it means two parallel wires carrying currents in the opposite direction, they repel each other. So this is very, very important. So two parallel wires carrying current in the same direction attract each other, whereas two parallel wires carrying current in the opposite direction repel each other. And direction is given by Fleming's left hand rule, and direction of magnetic field is given by right hand thumb rule. So expression for how much force is acting between them, either currents are same direction or opposite direction. So we can find magnetic field due to wire P at wire Q. Magnetic field is given by wires are infinite long carrying current. So magnetic field due to straight wire which is infinite long and carrying current B1 is given by mu naught I1 upon 2 pi r. So this will be magnetic field at P1. No, we have to find force on P1. So this is the magnetic field mu naught I1 by 2 pi r at P1. Then magnetic force, we have proved F is equal to BIL. Sin 90 is 1. So F is equal to BIL means magnetic force acting on P1 which is outward will be equal to B1 I2L, because B1 is the magnetic field which is external magnetic field on Q due to wire P. Magnetic field into length of wire into current through the wire Q. So B1 I2L, or F is equal to mu naught I1 by 2 pi r into I2L. Or from here we can find force per unit length. So mu naught I1 I2 upon 2 pi r, and this force is mutual. It means force experienced between two parallel wires carrying current in the same direction or in the opposite direction, it is mutual. So it comes out to be force per unit length mu naught I1 I2 product of currents over 2 pi into r, perpendicular distance between the two. So this force is mutual. And from this force we can define 1 ampere. What is 1 ampere of current? Suppose I1 is equal to I2 is equal to 1 ampere. That is, suppose 1 ampere current is flowing through the wires, maybe parallel or anti-parallel. Then suppose R1 is equal to 1 meter, R is equal to 1 meter, mu naught, value of mu1 naught is 4 pi into 10 to the minus 7 SI units de which. Then F by L will be equal to, सबसे value of mu naught 4 pi into 10 to the minus 7 into I1 1 into 1 upon 2 pi into 1. So simplifying it, we get 2 into 10 to the minus 7 Newton per meter. So it means we can define 1 ampere. So 1 ampere current is said to be flowing through each wire separated by distance of 1 meter when a force of 2 into 10 to the minus 7 Newton per meter is acting between them, may be attractive or repulsive. So from this we can define 1 ampere. So 1 ampere current is said to be flowing through the two parallel wires separated by distance of 1 meter, and the force per unit length between them is 2 into 10 to the minus 7 Newton per meter. So the 2 into 10 to the minus 7 Newton per meter force होएगी दो parallel wire ਦੇ ਵਿੱਚ, ਤਾਂ ਅਸੀਂ ਕਹਿ ਸਕਦੇ ਹਾਂ the current flowing is 1 ampere through each wire. So this is all about magnetic force experienced by a conductor carrying current placed in the magnetic field, or force between two parallel wires carrying currents in the same direction or opposite direction. I repeat, two parallel wires carrying currents in the same direction separated by a small distance, they attract each other. Whereas two parallel wires carrying currents in the opposite direction separated by a small distance, they repel each other. So question may be asked, okay, why two wires carrying current in the same direction attract and whereas two electron beams traveling the same direction repel each other, because in case of wires carrying current, force is due to interaction of magnetic field produced by one and on the another wire, and wires are not charged. But in case of two electron beams, electrons are negatively charged, so they repel each other. So this is all about magnetic force. Thank you. All the best. Be happy. Stay tuned.